Good morning, friends. Today we're going to start working in 3 dimensions, and we're going to make a landscape like this one, and we're also going to make a little solar system model as we try to understand how this space is working. And a key thing to understand about 3 dimensional space is obviously on a flat screen it doesn't really exist. We're just pretending. We're projecting these volumetric spaces onto a flat plane. And of course, all kinds of distortions get introduced into that. The math can get a little bit challenging, um, even for something pretty straightforward like projecting a point onto that. Um, but P5 is, in my mind, one of the easiest ways to get involved. Another way is with Blender, which is a free software you can download. It's super richly featured, and in fact, it's used. It's I think becoming kind of an industry standard. Lots of great projects. Lots of really impressive projects have been made with Blender, and also YouTube is full of tutorials on the subject. We're not going to officially use it in this class because we're really focusing on the code of it, but you can use it to make models and bring them into P5. And also, if you find that this code-based approach just isn't for you, feel free to use Blender. I'm just not going to be teaching the software because I think it's pretty easy to pick up. And I think that the things that we're going to learn about working with 3 dimensions in P5 will actually really help you if you are interested in or prefer to use Blender or Unity or whatever environment you prefer. So what I'm going to do is just start with kind of an empty sketch. Um, and you can maybe pause the video and get yourself into an empty P5 sketch. I've just made a canvas width equal to window.inner width and canvas height to window.inner height, as I so often do. And I've got this setup function with this create canvas tag. Or function, and I'm passing in the canvas width and the canvas height, and also this new third parameter, which is webGL. And what that third parameter does is it gives us direct access to the GPU, and it allows us to render things in 3 dimensional space. Because when we're making sketches like this, simple as this sketch, is, there is, as I said, a lot of math that goes into projecting these forms, each point of these forms, as they move through space. And once we add in things like if we want to actually make these look like planets, which we can do, and it will do in a few days, then it gets and add lighting. Lighting is very computationally expensive because what lighting introduces is just a bunch of little data points bouncing off of these objects and recalculating how the light is interacting with each object. And it's all pretty neat, but it's very computationally expensive. And that's why we have these things called graphical processing units that I'm sure you've heard of. And this video, which is on the syllabus, a link to it, sort of demonstrates that. I queued it up to the key moment of truth where they compare or they in a way demonstrate how this GPU operates. So instead of drawing each pixel one by one, what the GPU allows us to do is to do something like this, where we draw every pixel at once. So you can draw the whole image, sort of not instantaneously, obviously, but in parallel processing. And we'll get more into that as we get into shaders. But it's very powerful, and that's this webGL. And so what webGL literally allows us to do in P5 is to draw not just and I'll go ahead and do this in the draw loop. So I'll make a draw function. So we're familiar with the idea of having, let's say, a fill, and of drawing an ellipse, where we would say, and I'm just going to say 0, 0, and give it a size of 100. And we'll take a look at that because this will demonstrate something that's very important to understand about the webGL canvas is that the center, the 0, 0 is not up here anymore in the top left. The 0, 0 is now in the center of the canvas, which is helpful, but also can lead to some confusion. So remember that when you're in webGL, you're always working with a 0, 0 at the center. And this is just an ellipse. It's an ellipse as we've seen before, but this space that it's being rendered in, and I'm going to go ahead and give this a darker background because I just like it better. The space this is being rendered in is actually 3 dimensions, and we can see that if we rotate this. So I'm going to resize these windows a little bit, and then we'll be able to go back and forth. Alrighty. And I hope you can still see that text. Resize this window, recenter it rather. And here I'll actually go ahead and make this a little bit bigger for you too. So now we've got our ellipse, and if I rotate it, rotating an ellipse isn't all that much fun. Because it doesn't really look like it's rotating, right? If we just call rotate, and we'll just say like rotate it by an angle. We'll increment the angle, and I'll initialize that angle. So I'm going to call this transformation function called rotate. But you can see it doesn't really look like it's doing anything because that's a circle or a circle-ish thing. One thing you notice in webGL is you can see how this circle maybe doesn't quite have enough points. So if we did zoom in a little bit, and we can do that using the translate function. And I'm going to translate this. Let's see, I'm going to go to 500. So we should be right up close on that circle. And now you can see that it's actually rotating because we've got this sort of low resolution on this ellipse. It doesn't look resolution on a 2-dimensional canvas, but on a 3D canvas we start to see those irregularities. And as I'm sure you know, circles are always imaginary things. They always have these. They're always just complex polygons. But if we polygons, but if we give them enough points, they appear round. Now I can also rotate this. Now that I'm in 3 dimensions, I can rotate this on the x-axis, and we see. I'm going to zoom back out. We see now we're rotating that ellipse, and it was looking jumpy because the center of the camera that's trying to perceive. If we go back to this model, this camera, this imaginary camera position right here that's really framing our view, is in P5 located at negative 500, so 500 back. So when we move 500 up, we get right up to where that ellipse is actually positioned. And so it's kind of freaking the GPU out. That shouldn't really happen. This is a bit of a glitch somewhere in the code, but there it is. So if we move just not quite so far in, we can see now we're getting that rotation. And if we move even farther out, there's something closer to what we were hoping to see. And maybe I'll just set this rotation a little slower so we can see that really better. And I think if we move in a little bit, it won't look quite so jumpy. I know it still does. So you can see it's rotating actually around a point. As we move out, it doesn't really appear to be quite the same. So I think again, I think that to me, to my mind, reads like a glitch. So take, there are definite glitches that will occur in especially in this webGL mode of P5. Um, but that's all part of the fun, isn't it? So now I'm rotating on the y-axis, and you can see, so the x-axis, rotation, the x-axis is going to be along this path, and the y-axis is going to be along this path, just like in two-dimensional space, right? And so when we're rotating around, when we call rotate, we're rotating around that axis. So you can see that's rotating around this up and down axis. And now if I rotate in the z dimension, which is this magical third dimension, you can see now we're rotating in the z dimension, which is actually coming towards us. So again, if I zoom in a little bit, we can see it's rotating on the axis that's coming towards us. So it's rotating, you know, sort of in a way that we can only barely see from this angle. But we can do more than just ellipses, obviously, in 3D space. We get a whole new class of shapes, and I put a link to a couple of them on the syllabus. But one is called sphere. And all these shapes, they take between 1 and 3 arguments, but all of those arguments are related to the size. So this sphere is going to be 100, and you can see, now you can see the rotation on the z-axis much more clearly, because we see this sphere is actually a bunch of triangles, and all 3D geometry, or in most rendering engines with 3D geometry, I guess with that caveat, but practically all 3D rendering is done using triangles. And so we compose other shapes out of these triangles. And maybe now you start to see why it would be computationally expensive to have a lot of these. And this is not a very high resolution model. A lot of models will have, thousands and millions of thousands of these triangles to make shapes that appear organic and natural looking. So we're not going to get into lighting or anything like that today, or the skinning, and we're going to keep with these simple shapes. But I think it'll be a good and interesting introduction to how this space works. And I'm just going to move back to 0, 0, 0 on this translation axis. So we can talk about what this means. We've already done here 2 transformations. So I'm rotating, I'm translating, and on the P5 reference, we can see there's a category of functions that we have access to called transform. And that's one of the key things I want to talk about today, is this transformation matrix and how it works. So you can see there's rotate. Rotate is typically for rotating in 2 dimensions, so we can give rotate an X and a Y, and we'll use that primarily on this 2D canvas, where we would give it an X and a Y and draw something like a rectangle. When we're working in 3 dimensions, we're rotating on one of the 3 axes, as I was just showing you. We can also scale, and we can, very importantly, translate. So I mentioned that this sphere just has a size, and so it's being positioned by default at 0, 0. And if I want to add another sphere to this, I'm going to give it a different size, or I'll just say sphere of 50, and I'm going to give it a different fill color. Let's make it blue. And so it's going to be half the size of the other sphere, and it's going to be blue, but you can see we don't see it because it's the center. It's right there. It's inside the other sphere. If I get rid of this sphere, you can see there's our blue sphere. Now, in order to move this around the canvas, what we need to use is this translate function. And the way these transform functions work is they're cumulative through the draw loop. So if I translate this sphere to negative 200, and I translate this sphere to 200, let's see what we get. Oops, that's not it. That's it. Oh, where did my blue sphere go? I don't know where my blue sphere went. Oh, that's funny. I didn't I was changing the I was changing the color, not adding a translation. I'm going to translate the green sphere, and now this is actually a good example of this in action. You're like, I translated the green sphere over. Where's my blue sphere? Shouldn't that be at 0, 0? But no, this translation is affecting both the green sphere and also the blue sphere. So the blue sphere is still inside of this green sphere. And we're also seeing that this rotate z is being applied to this sphere as well. Now, it's no longer rotating in place as it was when we were at 0, 0, because the rotation center for this rotation is 0, 0. So when I move this sphere over here, it's now no longer rotating around its center, it's rotating around the center of the entire transformation matrix. And I hope that's clear. If it's not, don't worry, we'll get a little practice at it today. And sometimes this idea takes a little while to really get comfortable with. I know it took me probably years to really come to grips and get comfortable with all these things we're going to talk about today. But I'm a slow learner and poor speaker, as you know. So I think you'll probably be able to get it a lot quicker. So if I translate my blue sphere, I'm going to translate this back over 200. And now we see the blue sphere is back in the center. So we translated the whole canvas, or the whole camera, or the whole, page that our canvas, our stuff is getting drawn on. We moved like the whole page over 200, and we drew this green, and then we moved it back to the center, and we are now drawing this blue. So you can see the green is now rotating around the blue, and the blue's rotating around the center. They're both rotating around the center, but it appears like the green is rotating around the blue because the blue is at the center. Now, there's one really neat thing we can do if we want to sort of alter this behavior in sensible and useful ways. And that is to use something called push and pop. And so with push and pop, we can isolate a transformation. So now we've got this rotation that's rotating. It's rotating around this center, and this sphere has been moved over 200, and this sphere has been moved over 200 to the other side. So we can see that this sphere is no longer at the center because we pushed the state of our transformation matrix with this push call, and we did this other translation kind of in an isolated silo, and then we popped, which means we popped it off. The easiest way, I think, to think about this now, if you're not coming from a hardcore data structures and algorithms background, the easiest way to understand this is just think of it as like when you push, you're going into a separate transformation space, and when you pop, you're coming back to the original one. And I can also move this rotate Z over here, and we'll see now we moved the center over here, and we're rotating around that center. We're also not rotating this blue sphere anymore because all these things are happening inside this push and pop. So all we're doing is translating that blue sphere. So I hope that makes sense, and that's what we're going to use now to make this. I mentioned I want to make just like a little solar system with you to kind of understand these ideas a little bit better. So what I'm going to do is I think I'm going to start by we'll skip that for now. What I'm going to start by doing is just making something that we can call the sun, and I'm gonna make this yellow, and it's gonna be a sphere, and let's just call it 200. So there's our sun, and I'm gonna get rid of this stuff here. I'm gonna keep this angle for now, because we're gonna actually use that to make our planets rotate around this sun. And we've already got these 2 planets, but I just deleted them. I don't know why they're there anymore. But those seem like a good start. We need like a blue planet, I think, which would be the planet Earth, and probably a red planet named Mars, and I don't know what color to give Mercury. And then we'll need planet Venus. Of course we will. And so we're going to have a number of planets, and I think it's probably best to write a function. And in this function, we're going to have we're going to do those things that we were just doing, right? Which is have a fill color, and we'll have a sphere. And the sphere is going to take then a size and a color. So we'll pass those in, right? A color and a size. And we'll also pass in, since these are going to be, we're going to make these planets, and I think I still have this one running here. We're going to make these planets be rotating around the sun. So I'm just going to pause for a second and let you think about what we've learned already in other classes and videos that will enable us to do that very easily. And after a pause, I'm going to say, yeah, we're going to use sine and cosine, right? So what we're going to have is probably an x value that's going to be determined by a distance times the sine, of an angle, and we're going to have a y value that's going to be, and you know what, let's just make this distance. I just don't want to have any collisions with, inbuilt P5 functions, but I think theirs is called dist, actually. So we're going to have a y that's going to be the distance times a cosine of an angle. So we're also going to want to have that angle come in. But before I bring that angle in, I think what I'm going to do is use those x and y values. Holy cow. Why would I want to transport steam controller? I don't even know what that is. VS Code, I tell you. So we're going to use that x and that y and that z and it translate. And I bet you can know now, after what we were just talking about, that what I'm going to want to do is push and pop this. Because I'm going to want that translation to apply just to this one sphere. So we're going to pass in also that x. Oh, no, the x and the y we're making, we're going to pass in that distance. And I'm going to do something that I think is very useful, which is to use an object. And we've made a lot of objects, data objects, using array.from. But I think in this case, I'm just going to make it like this. So it's going to be an array, and it's going to be an array of objects. And each one is going to have a distance. And for this first one, maybe we'll say 100. And what else is it going to have? It's going to have a color. And this first one, I think I'm going to go purplish, right? It's that little one there. 220, 20, 220. And then I think there's a size, and the size here, actually can't remember what that was. I'm not looking at my code right now, but we'll just call it 100 for now. And then we need to just make, we're going to make 4 of them. We'll just do the inner solar system. And so this one, you know, maybe we'll go like 200. Since we're not using an array to make these, we can be a little bit, have a little bit more fun with them, with these numbers. And this second planet is going to be green. It's going to be Venus. And let's actually make this first planet really small, and this one a little bit bigger. And we'll say 100. I would say 70. And then the blue planet, this very nice blue planet that we live on, we can make that be 350 away maybe. And we'll give that a size of 100. And then finally we'll have our red planet, the well-known Mars, and we'll put that out there at 500 and give it a size of 980. I think it's actually probably bigger than Earth, but maybe we should reflect that. I actually don't know. Is it maybe about the same size as Earth? You let me know. So now we've got this array of planets. We've got some distances, some colors, some sizes, and we can bring those in to draw a planet. What I'm going to do is I'm going to show you a nifty little trick that I really like, which is called in JavaScript object destructuring. And what I can do is pass into this function, pass in a planet, which we'll get from our old friend array.forEach. So we'll say planet, and we'll just draw that planet inside there. Now, that each one of those is going to be one of these objects, and so it's going to have a distance and a color and a size. And instead of saying planet.distance and planet.col and planet.size, what I can do is just destructure those names off of that object, just like that with those curly braces. And that'll work just the same as if I had passed in each one of those parameters. So I'll pass in the whole object and pull those keys off of it. So that's a really useful little thing. Now each time we're going to be pushing and popping, and I'm going to go ahead and open that. So we're trying to make this thing over here. We'll see how far we've gotten so far. And we've gotten pretty far. Look at that. We're already rotating. We've got our planets. Somewhere in there, I'm thinking there's probably behind the sun there is going to be our Mercury. In order to see them all, what we want to do is not translate those on the Y, but we want to make them come towards us. So the circle we want is going to be the X coordinates are going to be the X coordinates, but what we're currently registering as the Y coordinates, so it's registering this top to bottom. We want to go from behind the sun to towards us. So we're going to move this. I'm going to move this Y over to the Z. And now we're moving just like we want to be. And I think we can see what's happening there is that our sun is so big in relation to our planets. We need to be at least as big as this sphere, which is 200. That's our sun. So I guess what I need to do is start this distance at 250 and then 325 and then 450 and 6. So let's just see now. Now we're getting all those planets. They're still kind of jammed up there. I should probably make those sizes smaller is what I should do. So let's make this be like 10, 30, 50, 40. And now we've got some planets. Yeah, they're all there. 1, 2, 3, 4. And as we come around back towards us, we'll see. Sure was over there for a while. We'll see that we're actually inside of where Mars is going to go, I think, behind us. We can see Earth, right? No, Mars is still in front of us. So we can play with those distances if we want to, but it's not important, really. That's really most of what I wanted to show you with this example is just how these rotations work, how these translations work, and how we can utilize push and pop to make sure that our translations only occur to that one planet. We can also make these planets rotate. So I would put that rotation not out here in the draw loop, but inside this push and pop. So each one will rotate at its own speed. And let's just say we'll just rotate around the y-axis, and we'll rotate, we'll say angle divided by size or something. So now they'll have their own sizes. That's not quite what I wanted. Put this after this translation, and it's still not rotating very much, is it? So let's do size over angle. Let's see. Our angle time size. Oh, I got that rotate y right. Oh yeah, they're rotating. I just wasn't seeing it right at first. So we see they're rotating. We could put those off axis if we wanted to a little bit. We'll rotate Z, and one thing we can do is put our angle mode. Our angle mode, I think, is by default in radians. So let's just do 0.2 or something like that. And so now they're all a little bit off axis, which is how we expect planets to look. So that's enough for this video, I think. Just meant to be a real quick introduction to these ideas. In the next video, we're going to come back and we're going to make something more like a landscape. And so we'll have a ground plane, we'll make a sun, and we'll talk about that. And what I want you to do for today's assignment is to make your own landscape.